That's good. Right, I hope you're going to enjoy this little talk. I'm going to tell you a little bit about where I work, which is a place called Jodrell Bank, which is part of the University of Manchester, but it's about, 15, 16 miles, 25 kilometres south of here. It's an interesting story, I hope you'll agree. There'll be time at the end for a talk, for a few questions, I hope, as long as I don't blather on too much, which is one of my usual problems. Okay, the sort of observatory at Jodrell, down at Jodrell, so 25 kilometres south of here, is dominated by this telescope, the Lovell telescope. So this is a giant radio telescope, and this is a beautiful drone film of it here. It just shows you how it stands out as a landmark in the Cheshire countryside. So you can see it all the way from, if you stand up in the Peak District on the hills and you look west towards Liverpool, you can see the cathedrals of Liverpool on the horizon. And the only thing really that you notice, particularly on the Cheshire Plain in between you and Liverpool, sort of 50 miles away, is the Jodrell Bank telescope. So an incredible thing. It was the biggest in the world when it was finished in 1957, and it's still the third largest fully steerable telescope in the world. It's about the same height. If you stood next to that telescope, if you put next to that telescope the clock tower, the Big Ben clock tower at the Houses of Parliament, it's within about a metre of the same height of the spike on the top of that tower. So it's a huge thing, about 90 metres high or so. And that's what makes it so powerful, is basically its size. It picks up radio waves coming from outer space. This is another shot of Jodrell Bank from the air. This is a lovely view of the whole site. It shows you the big Lovell telescope on the left there. But just to emphasize to you, it's not just a research center where we do astrophysics research. It's also a public visitor facility, so you can visit that site. There's a public visitor center there. And it's also, in the last few years, been made a UNESCO World Heritage Site. So a very unusual thing. I'm not quite sure there's any university in the world owns a UNESCO World Heritage Site other than this one. So it's a nice thing to have. We are up there somewhere on the horizon, in the gloom of the horizon up there, about 25 kilometres north of Jodrell Bank. And some of us work at Jodrell Bank and some of us work in the Alan Turing building, which is up just over on the other side of campus here. And just to sort of identify for you a few of the things there, there's the Lovell telescope on the left, there's the Mark II telescope on the right. That's part of a big network of other telescopes we run across the country. And in the middle is the little control building where the astronomers work. And next door to us, we have the visitor facility, the Jodrell Bank Centre for Engagement. And we also have the global headquarters of a new telescope project called the Square Kilometre Array. So we've been involved for many years now in designing and now in the later stages of construction of a whole bunch of telescopes out in South Africa and Australia, where basically there's fewer people out in the deserts. The sheep don't have mobile phones yet, and so there's less radio interference, and so we're building a giant, powerful radio telescope there. But the international headquarters for that project is here at Jodrell Bank. The visitor centre looks like this, a beautiful new building. I don't know who's been to the visitor centre at Jodrell recently. Not enough of you, I would say. So this is something for you to go and do. Go and visit there. It's a great place. This is the new building, beautiful photograph. It's aligned north-south. So this is a photograph taken by our computer manager looking north, a time-lapse photograph, and it shows the stars wheeling around the North Celestial Pole, around the pole star, as the Earth spins. And inside there's an amazing exhibition telling the whole story of Jodrell Bank, using some of the material off the original telescope. So I mentioned we didn't just have the stuff at Jodrell, we've also got a bunch of telescopes across the UK, or across England in fact. So over about 217 kilometres we've got 7 radio telescopes. 2 of them are at Jodrell that I just showed you, but another 5 are spread across the country, and they're all connected with an optical fibre network. And together, they work together basically. They all point at the same thing at the same time. And the signals from them are collected and they're sent down this fibre network and they're brought back together in a computer at Jodrell Bank where they effectively make pictures of the sky, the invisible sky, the radio sky, that would be an equivalent sharpness to what you would get if you had a telescope that size. So if you had a 200 kilometre size telescope in the middle of England, we effectively synthesize, we recreate what that telescope would see with these 7 dishes. I think people in Birmingham, we wouldn't have got planning for the big one, for the 217 kilometres. People in Birmingham would have moaned to high heaven, I'm sure. But anyway, we do that with these seven telescopes. We go beyond that as well. We go right across the planet. We have something called the European VLBI network. We're very inclusive because we don't just include telescopes in Europe. We have telescopes all the way across the world, out to South Korea and out into China and down into South Africa. And they basically do the same sort of thing, except we create a telescope now the size of a planet. And the farther apart you spread these individual telescopes, the more of a sort of zoom lens effect. You zoom in on the details of things in distant space. Here's my colleagues, or at least some of them. There's about 170 of them. If we could get them all in one place, they would probably collapse and create a black hole, actually, if we all got in one place. But that's some of them standing out at Jodrell Bank from a meeting a few years ago. So I'm going to start with the beginnings of Jodrell Bank, the early days, and tell you a bit about why that telescope is called the Lovell Telescope. It's named after Bernard Lovell. Bernard Lovell worked here at Manchester. He was in the physics department, which is what we're still part of, the physics department here, before the Second World War. That's a photograph of him taken in 1939. Of course, when war broke out, a lot of physicists and other scientists were brought into the war effort, and his role was to work on radar, development of radar. So sending out radio waves and getting an echo back, bouncing back off something. So in particular, he led a team. You see him there with his team sometime during the war. We're not sure when that photograph was taken. He led a team that developed a type of radar that was used to sort of image the ground. So initially it was used for detecting U-boats or submarines that were surfacing at night. And they played a major role in finding these things at night because the radio waves could see them in the dark, and helped win the Battle of the Atlantic, so protecting the convoys and so on earlier in the war. Later in the war, actually, they used various techniques to improve the radar all the way through the war. In 1943, they fitted the radar onto landing craft that were used in the landings in Sicily and Italy, and the mainland of Italy. And then a development of that was used 80 years ago this morning on the landing craft that landed on the Normandy beaches. So they had a radar on the landing craft controller that scanned the horizon, and they could map the shape of the coast. So they could see that at night as they were coming across at night, and they could get themselves into exactly the right place they needed to be to send the landing craft onto the beaches at the right point. So it was a major important role in the war. At the end of the war, he was basically told to go back off to the physics department. I remember he told me once that he'd been used to ordering up 2 Lancaster bombers, and they were arriving the day after, and the next week he came back to the physics department. He couldn't get a screwdriver out of stores, so it was a bit of a shock to the system. But he came to Jodrell Bank and he thought, oh, what am I going to do? Oh, maybe I'll use this radar thing that we've just invented to do some physics. And so he wanted to look at particles that arrived in the atmosphere from outer space, moving at nearly the speed of light, called cosmic rays. And as they came through the atmosphere, they would leave a sort of trail behind them that he thought he'd be able to bounce these radar signals off. So he borrowed some radar kit, and he set it up actually just in the road, just over there, over these buildings over here, the next road along, Coupland Street. And he couldn't get it working because there were trams, electric tram trolleybuses or something running up and down Oxford Road there, and the sparking from that was producing radio waves, which was drowning out his signals. So he asked around, he went in the senior common room as was, and he asked around, said, is there anywhere I can go? And they said, oh, go speak to that person over there. It's the head of the botany department. Down at Jodrell Bank, this place about 25 kilometres south of here, there was a little botany testing grounds, and he said, okay, you can go. You can take your stuff out there and try it out there. That picture there on the right is a picture Lovell took himself on the first day at Jodrell Bank with the ex-friends and things from the army helping and the local farmers helping. You can probably identify which ones are people in the army and which ones are local farmers from that picture on the left. The ones with the wellies are the farmers, and the flat caps. Oh, they've all got flat caps. So they're pushing stuff into the muddy field and they're setting the thing up. He was given permission by the botany department to stay for 2 weeks, and we never left. He never got that permission extended. In fact, I'm pretty sure they forgot he was there for a while. We don't do that these days, obviously. So while they were there, they basically invented a new science. And that new science was called radio astronomy. It was seeing the universe with radio waves. And this is an article I quite like from the Manchester Guardian, as it once was. With its overcast skies and smoke, Manchester could scarcely be regarded as a paradise for astronomers. It was pretty smoggy and grimy, much more so than it is today in those days. Of course, we still deal with clouds, but the advantage of the radio waves is the radio waves pass through the clouds. So in fact, we can do this, studying the universe with radio waves. We can do it through the clouds, we can do it during the day, and we can do it at night as well. So we can do radio astronomy effectively 24 hours a day. He soon realized that he couldn't actually detect these cosmic rays, these things he was really interested in. It's what he'd been working on before the war. He didn't actually manage to get any signals. Instead, what he got was echoes from meteors, from shooting stars. So dust particles burning up in the atmosphere. Have anybody seen a shooting star? So if you see a shooting star, it's just something burning up in the atmosphere above your head. So he got echoes from those, and they did a whole load of work on that. But he realized then that maybe they realized there was actually radio waves coming from farther away in the universe. So not things we were sending out and getting echoes back from, like radar, but stuff that was being generated in space and just arriving here. So that's what led to that big telescope being built. And an incredible thing to do, actually, certainly in those post-war years as well, just an amazing sort of ambition. And I think really stemmed from what he'd done during the war, really, his sort of experiences and sort of we're going to do it type attitude really helped him there. It was a problem. It didn't really go to plan. Nobody else had done anything like it in the world before, so they were changing the designs all the time, sometimes for reasonable reasons, sometimes for secret reasons, as we'll see in a minute. But basically, by the sort of middle of 1957, people were on strike. There was no money left to finish the telescope. It looked like a disaster. I've just got a little recording of Sir Bernard, as he was then, talking about how that crisis was averted.
I said to Henry Brown, we need a miracle to save us. Well, that kind of miracle came on October the 4th, a few weeks later, 1957, when the Sputnik 1 was launched.
So the miracle that saved them was the Soviet Union launching the very first artificial satellite, Sputnik 1. And the reason was because they used the radar fitted to that big telescope to track the rocket that carried Sputnik into space. They managed to get it finished to do that. The reason that they were interested is because that rocket was actually an intercontinental ballistic missile. So at that time, obviously the Soviet Union had a whole bunch of these things fitted with nuclear warheads. And the interesting thing, the worrying thing from the perspective of the West, was that they'd been able to launch something into orbit, and what might they next launch into orbit? So what they demonstrated with this was that they could effectively detect missiles with radar on an instrument like that giant telescope. Now, I'm going to move on because that starts us on to the next phase of things, because that brings us into the Cold War, the era of the Cold War. And there's a few things to say about that, and one is about the operation of spies at Jodrell Bank. This story really has only become public knowledge in the last few years. There was always rumours that Jodrell Bank were involved with GCHQ, which is the UK's secret intelligence agency, who does interception and were involved in things like Bletchley Park and so on in the war, but none of us really knew whether it was true. So when we were designing our new exhibition down at Jodrell, I thought, how do I find out if this is true? How would you get in touch with GCHQ? I thought to myself, I'll go to their website. Sure enough, there's a web form on the website. You can send them a message. How do you get in touch with secret spies? So I sent them a message, I've heard rumours that Jodrell Bank used to work with GCHQ. Is this true? Would you be prepared to talk to me about it? Send. A few days later, a reply comes back from the historian, David Abratat, who said, I saw your message and I went to have a look. And yeah, you're right. We did work with GCHQ. And in fact, somebody went to Jodrell Bank. We didn't realise this at all. So as soon as Sputnik was launched, a staff member from GCHQ went there. And there was then a long relationship. We're still not entirely sure, I'm not entirely sure, when that relationship ended. I'm pretty sure it's not happening now. but it didn't. It certainly went into the mid 80s, maybe early 90s at least. And one of the reasons I'll say that is because of the clothes that the GCHQ staff are wearing in that bottom right-hand photograph, because those look that sort of era to me. I'm sure I had a jumper like that. And basically the point was, what was interesting was that the Soviet Union effectively had all this technology that they were putting in orbit, and the West, if you like, wanted to know about what that technology could do. And one way of doing that was to eavesdrop, to intercept signals that were being sent. And a really good way of doing that was to have this big telescope that could collect these weak signals. So there were regular visits all the way through the late 1950s, 60s, 70s, and so on. There were only a few people at Jodrell Bank who knew about it. These are three of them. Bernard Lovell on the right there. His deputy head of department, if you like, was J.G. Davis in the middle. And then the sort of technical person involved was Bob Pritchard. And so there were three of them. There was maybe one or two other people who knew about it. And they basically, were fed information about when these things were happening. Some of them were in the public domain, but many of them were not. One of the things that it did around that time, the telescope, was it was on standby to be used during the Cuban Missile Crisis. So when the Soviet Union put nuclear missiles onto Cuba in 1962, this was very worrying for the USA because they were very close to the USA. And perhaps the closest we came to having a nuclear war. But at the time, our radar defense systems that would give us the warning of nuclear attack were not finished. Filingdales on the North Yorkshire moors wasn't finished. The people there were on strike as well. Spotting a theme. They asked if Jodrell Bank could be used. So there were RAF teams trained to use the telescope. There were radar stations installed at Jodrell Bank. And it was ready to basically swing east and look. And you can look in the logbooks now, and you do see in the logbook all the training sessions down as RAF. The final weekend, it didn't get used. And I think one of the reasons was nobody wanted to raise the sort of threat level by apparently getting ready. Because what would have happened, of course, although if you spoke to Lovell about it, he'd say it would give people a 4-minute or 7-minute warning or whatever of nuclear attack, and they could get into the bunkers. Of course, there was only some people who would get into bunkers. The vast majority of people wouldn't. And the real reason for a warning is that you can get your own V bombers, the Vulcan bomber fleet, into the air off the ground before the nuclear missiles arrive, and that gives you the chance to strike back. And that's the sort of basis of this mutually assured destruction approach to nuclear weapons. So Jodrell was sort of involved in that, and of course we're all very pleased that it didn't have to be used. There was this sort of uneasy relationship between Jodrell Bank and the Soviet Union. Lovell visited the Soviet Union, as did other colleagues from here. People from the Soviet Union came to Jodrell Bank. That's a photograph taken at Jodrell Bank with Alan Masevich, who was a very senior astronomer in the Soviet Union, responsible for their optical space tracking networks. And they were searching for their missing Venus spacecraft. They would always bring someone with them, of course, who was quiet and apparently couldn't speak English, but when you caught them out, they were speaking English in the background, who would keep an eye on what was going on. And of course, the same was true when people from here went there. It was very sort of uneasy, well, we'll go there, you come here, and people are learning a bit about each other. All the time actually still doing real science, so collaborating on the science, independent of the politics, but the politics was always there in the background. This is a sort of interesting, I don't often look at this newspaper, but this is an article in the Daily Express that from a few years ago, which is a picture of, there's Lovell and Alan Masevich in the Soviet Union. And this was quoting a KGB agent, actually, not that long ago, ex-KGB agent, saying that basically her role was to try and persuade Lovell to defect. In fact, when he visited the Soviet Union, they did ask him to defect, and I've just got a little recording of him telling that story.
I was given a luncheon by the president of the Academy, Kurdish, and he asked me about this, and I said, well, we're trying to build this big telescope. And he said, how much money do you want? I said, about £5 million. He thought for a few moments. He said, we want you to remain here. We will build the telescope for you. We have plenty of money. And I said, President Carrish, I'm an Englishman, I wish to return to England.
So they did let him go. There were other people there who certainly weren't let go, and it was a very tense time for him. And he was very ill actually after that visit because of the sort of stress of it, I think. Now all that story, that was an excursion onto the Cold War, just stimulated by the Sputnik rocket, but it's not what Jodrell Bank was really supposed to be doing. We were supposed to be looking at the radio universe, the invisible universe. So I want to finish most of the talk now. The rest of the talk will be about that. So what do I mean by the invisible universe? Here's a lovely photograph of our Mark II telescope, which if the Lovell telescope didn't exist would be everybody's favourite telescope. It's big, it's still a big thing. It just gets no attention from the one next door to it that's a bit bigger. But the Mark II telescope here with a rainbow overhead, again taken by our resident photographer and head of computing, Anthony Holloway. Beyond the visible rainbow, you've got the whole rest of what we call the electromagnetic spectrum. So out beyond the violet, you've got the ultraviolet, beyond that X-rays, beyond that gamma rays. And if you go the other way, beyond the red, you've got infrared, microwaves, radio waves. So what we see with our eyes is only this tiny bit of the universe. And that's true just even looking around us in the room now. There's more information, more signal here for us to see if we want to see it. So what we want to do with our telescopes, with the radio telescopes in particular, is you want to look at how the universe appears in radio waves. This is how it appears with visible light. So this is a picture of the whole of the sky. It's actually made with a spacecraft called Gaia, which is a European Space Agency spacecraft, just recently. So this is one of our best pictures of the whole of the sky. So what you've got to imagine with this is, do you know like maps of the Earth, the whole globe, when you sort of look at a map of the Earth in an atlas? Does anybody think the Earth's flat? We've got security on hand. Anyway, okay, so you've got this globe, and you sort of unpeel the surface of the Earth and you lay it flat in an atlas, and you see, usually we put, for, historical reasons, we're in the middle somewhere, and then you've got America's on the left, and Asia and Australasia in the bottom right. But this is the same thing. So if you wanted a full sort of idea, what you'd have to do is imagine looking straight ahead. In the middle, that's the middle of our Milky Way galaxy. If I sort of turn around to the left now, I'm moving towards the left of that picture. If I go all the way to the very left of the picture, is in that direction, directly behind you. And if I did the same from pointing at the middle and I went that way, I'd be going on the right on that picture and all the way around until I get to the same point, pointing that way. Same with up and down. If I point in the middle and I go up to over my head at the top edge of that picture and down to below my feet at the bottom edge of that picture. So if you want the full effect, you have to get hold of this at the left edge and at the right edge, and you have to wrap it right around your head. I do this sometimes on a quiet evening at work when nobody else is around. So this is basically the whole of the sky around us. The dominant obvious thing is our galaxy. We are in our galaxy, the Milky Way. And this is a picture that's arranged so that our galaxy is like a disk. It's like two dinner plates put face to face, or two frisbees put face to face. And we're sort of 2/3 of the way out for the middle inside that disk. So if you can now place yourself inside that disk and imagine what the universe would look like looking around you, if you look within the disk, you see loads of stars. If you look straight out of the plane of the disk, or the dinner plates, there's far fewer stars. So this is the plane of the disk of the Milky Way that's horizontal in this picture. The two blobs on the bottom right are actually the Magellanic Clouds, two dwarf galaxies nearby to our galaxy. Anybody seen the Magellanic Clouds with their own eyes? Somebody at the back. You need to go to the southern hemisphere. They're weird looking. They look like clouds in the night sky, these sort of fuzzy things, but they're nearby galaxies. Can't see them from up here. Now, what you do with the radio telescope, that light, that's all coming from stars. Stars a bit like the sun. They're hot, 6,000 degrees, the sun. Heat anything up to that temperature, it glows, it produces visible light. The dark stuff that's running through the middle of that picture is basically where there are dust clouds in space between the stars, and they block our view of the stars beyond them. So it looks like there's fewer stars, that's why they look black. It's just dust clouds. If you go to a radio telescope view of the sky, this is what you see. So on the same scale. So this radio picture was made with the Lovell telescope at Jodrell Bank. It was made with a telescope in Germany, and it was made with a telescope in Australia, so we could see the southern hemisphere as well. And what you see now, you see radio light. Now, the colours are not real, because radio waves don't have colour, right? So we have to use what you sometimes call false colour. The colours there are just graded so that the darker colours are where the radio waves are fainter, and the whiter colours are where they're brighter, and they're just going through shades of orange. So there's loads of ways you could make it look incredibly garish if you wanted, but they do mean something. They're not made up. They do mean something. It's just that they don't represent what you might think by colour. So if you look at that picture, what you see now is not the light from stars. Stars almost become invisible in the radio. These stars like the sun don't really produce much radio. So what you see instead is the stuff between the stars. So in our galaxy, there's electrons that are spiraling around the magnetic field of our galaxy, and that produces radio waves. And that's what's producing the dominant amount of radio in that picture there. I've got a little movie here that was made by some colleagues in the Netherlands recently, which shows you one of the advantages of moving from that visible light view to a radio view. And that's that, just like we can see through these clouds here with our radio telescopes, we can see through the dust clouds. So where the dust clouds there are blocking our view of the middle of the Milky Way, the radio telescopes see right through, and in particular, see right through to the center of the Milky Way, which is right in the middle of the screen. So that's changing to the radio, and now we're zooming in. And we're moving to this picture was taken with the Meerkat radio telescope in South Africa, which is a fairly recent picture, amazing picture of the center of the Milky Way. We keep on zooming, and we're getting to incredibly tiny patches of the sky now, and you see this dot appearing in the middle. And that is a picture of the black hole at the center of our Milky Way. So at the center of our Milky Way, there is a 4 million solar mass, so 4 million times the mass of the sun, black hole. And the light from around it, the radio light from around it, before it's sort of, you can't get light from inside the black hole's in the middle of that ring of radio light. So this is made with a telescope called the Event Horizon Telescope, which extends across the whole planet. Going back to that radio sky picture there, I just want to ring that thing over there. See this? There's a bright spot, right? And when they first started using these radio telescopes, like at Jodrell Bank, for example, you'd be scanning this thing around on the sky, and they used to look at it with a chart recorder. Who loves chart recorders? There's a few I won't say you're old like me, but you might be. Little pens on rolls of paper come out of things, and pens go, right? So when they drive the radio telescope across the sky, all of a sudden, boom, and they go, oh, what was that? And they go back again. Was it somebody starting up the car and the starter motor causing some radio waves? No, it was really there. So they worked out that there was actually these bright things in the sky. So they go to their friends with normal telescopes, if you like, visible light telescopes, and they say to them, what's there? We see this really bright radio thing in the sky there. And they go and they say, nothing there, can't see anything. So a lot of these things got called radio stars, they called them. They didn't have any idea what they were. That one there's in the constellation of Cygnus, the Swan, and it's called Cygnus A. So the brightest radio source in the constellation of Cygnus, incredibly bright in the whole of the radio sky. If you take a modern telescope, so a big modern visible light telescope, and you look at that bit of sky, what do you see? You see a whole bunch of stars, so the things with spikes on them, sort of the crosses on them, they're stars. And right in the middle, which is where Cygnus A should be, there's a fuzzy thing. So when they first noticed this, they thought it looks like two galaxies of stars coming together. These other stars in the area around are in our galaxy. We're looking through our galaxy into the distant universe. So somewhere out in the distant universe, it looked like two galaxies colliding. But when we got these networks of telescopes across large distances, like I mentioned before, we could zoom in, we could get sharp pictures in the radio, and the same patch of sky looks like that in a radio picture. So genuinely, if you look at it with your eyes through a normal visible light telescope, you see that. You look at it with a radio telescope, you see that. So something really weird is going on. Right in the middle, there's a dot. You can see the dot in the middle. That's in the middle of whatever that fuzzy galaxy thing was. But the most obvious thing are these two things shooting out either side. So what's going on there is that we've got a supermassive black hole in the center of this galaxy, like the one I just showed you at the middle of the Milky Way. In fact, pretty much all galaxies, we think, have supermassive black holes in them. And around that black hole, stuff is falling in and spiraling around, and it shoots material out at very high speeds. And it's a bit like firing like a hosepipe or something into a sandbox or something. Go psh! So this jet of stuff goes out and it splashes into the sand. This jet is splashing into the stuff around this galaxy, the gas that's sitting around the galaxy. And it becomes very bright, it accelerates particles to relativistic speeds, and it produces these radio waves. So these are incredible radio galaxies. So we sort of now know that the radio sky, rather than being full of stars, points of light that are stars, it's full of points of radio light that are actually supermassive black holes. So that's what the radio universe looks like. Things like this. I'll just show you one other radio picture of the whole sky, going back to the visible, just to ground ourselves in how our eyes work. So this is the visible galaxy. If we took a spacecraft, we built parts of it at Jodrell Bank a few years ago, and we put it into orbit with the European Space Agency, and we made a map of the whole sky in the microwave part of the radio spectrum. And we subtracted off that map with great difficulty and care all the radio waves that were coming from our galaxy and some of the other brighter radio sources. And effectively, when you do that, you get left with very little signal. But when you zoom in on that very small signal, very small radio signal, this is the picture you produce. So again, this is the whole of the sky. And the blue and the red represent fainter and brighter red patches of radio waves. So the whole sky is filled with this speckly pattern. It's what we call the cosmic microwave background. So everywhere you look, there's this hiss of microwaves coming from the distant universe, and that is the oldest light you'll ever see, because these radio waves set off from a time just after the Big Bang, so almost 14 billion years ago, and they've been traveling through the universe ever since, and we can map them on the sky. And in fact, those little blobs, those little sort of, that structure in there is the seeds, effectively, of the first structures in the universe, so from which the first stars and the first galaxies and eventually the planets and eventually us grew. So we see back in time with this picture, almost to the Big Bang. So this is the other thing about astronomy that's really cool. Having a telescope's like having a time machine, because you're waiting for the light to get to you. So if I look at the sun, which I shouldn't do really, but if I carefully look at the sun, then I see it as it was 8 minutes ago, because the light took 8 minutes to reach us. If I look at the moon, it's only 1.25 seconds ago. That's the distance to the sun in light speed. If I look at the nearest star, it's 4 years ago when we see it. So it takes 4 years for light from the nearest other star than the sun to reach us. So if you go back to something like this, you're looking at light that's set off from so far away, it's taken nearly 14 billion years to reach us. So the farther away we look, the farther back in time we see, so we get an idea of how the universe evolved. What I forgot to do was check the time. Who's got the time? Plenty of time. All right. So really the last sort of section I had was something about what the telescopes are doing at the moment, the Jodrell Bank telescopes today. So right this minute, and the weather's pretty good, we'll have a whole bunch of painters on the Lovell telescope, painting sections of it. So we have to maintain these telescopes. They're massive, big hunks of steel out in the weather, and they have to be looked after. And it's a major task, and it's something the university has been very good about over the years, is keeping our telescopes operating. So we have engineers who look after the telescope, go on the telescope every day. They know every noise that telescope makes, to the extent that if they walk out of their workshop on the far side of the site and they listen to it, they can hear it making a sort of creaking noise. They go, that's not a normal creaking noise. And they march over and they get on the telescope and they look around and see if there's a problem. Painters are painting at the moment on the Lovell telescope. Maintenance is important. As soon as it gets dark and the painters have had enough and they go home, then we go back to astronomy. And this is one of the things we'll be looking at tonight. And this is a recording of a signal. So what you're going to see is you're going to see the strength of the radio signal against time. So this graph. So here we've got the telescope pointed at one position, and then we just move it onto the object we're interested in. So now we're pointing at the object of interest. You may be able to hear it a bit. Because we can turn the radio waves into sounds, We don't pick up sounds from space with a radio telescope, we pick up radio waves. But just like your car radio turns a radio wave into a sound, we can turn these radio waves into sound, and this is what this thing sounds like. So, do, 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 do. Something flashing. When they were first discovered by Jocelyn Bell in Cambridge in 1967, the first one of these things she noticed, they thought, well, you know, that looks too regular to be natural. Maybe it's aliens sending us a message. So they called the first one LGM1, Little Green Man 1. And then they found Little Green Man 2 and Little Green Man 3, and then they thought about it a bit more and thought, no, we think we might know what's going on. So what is going on is that these things are the remnants of exploded stars. This is one of my favorite exploded stars. This is the remnant of a star that exploded in 1054, or at least we saw it explode in 1054. It exploded several thousand years before, and the light took that long to reach us, but we saw suddenly a bright star. And I say we, I wasn't around in 1054 despite appearances. It was seen by Chinese astronomers. So Chinese astronomers famously recorded this as a bright new star in the sky in 1054, nearly 1,000 years ago. If we look at it now, what we see is this with a visible light telescope. It's gas shooting out as a result of that explosion. But right in the middle of that object is one of these things, like I just showed you, that we call a pulsar. Basically, when the star explodes, it's the result of it runs out of fuel at the center, nuclear fuel. And because of those nuclear reactions were holding the star up against its own weight, it then collapses in on itself. So the central part of the star collapses to become a very dense object. The rest of the star explodes off into space. That dense object there we call a neutron star. It's about the size of a city. So it's about the size of Greater Manchester, about 20 kilometres across perhaps, but it weighs more than the sun. So it's like taking the whole of our sun, which is 100 times the diameter of the Earth, and squashing it down to be the size of a city like Greater Manchester. So incredibly dense, incredibly strong magnetic fields, and these things spin because the star originally was spinning, and as the central bit collapses, it spins faster, just like an ice skater when they bring their arms in, spin faster, they conserve angular momentum. The same thing happens to this star. So it's spinning, and it's shooting beams of light and radio waves out from its magnetic poles. And as it spins, it's like a sort of cosmic lighthouse. So this beam sweeps around the sky, and you see flash, 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 flash. That's what those peaks were. So they're really interesting things from the point of view of studying physics. They study extreme physics, and we now, we know of about 3,000 of these things now in our Milky Way galaxy. And what we're doing tonight is we're doing two things tonight. Two projects where we time the flashes arriving from these pulsars. We have a regular program where we look at a whole big set of pulsars, and we time when the flashes arrive, and we time them incredibly precisely. We've got an atomic clock that gives us an incredibly accurate time signal, so we can compare when those flashes arrive, when we thought they were going to arrive, to when they do arrive. That's going to let us do two things. We can study what the neutron star is made of. It's really dense. It's denser than an atomic nucleus, so we can study what's going on in that. And we're also, an amazing project is we work with colleagues across the planet with other radio telescopes. We look at a whole bunch of pulsars around us, and we know that there are supermassive black holes in these other galaxies. Sometimes galaxies collide. They certainly have collided in the past. These supermassive black holes spiral into each other and they collide. When that happens, the whole of space-time ripples. So there's gravitational waves that travel through the universe. So if they're traveling through us now, luckily enough, they're quite very, very weak. So what happens when a gravitational wave travels through us is we get sort of stretched in one direction, and then we get squashed in the other direction, and stretched in this direction, and squashed. That's what happens, this stretching and squashing. If you look at these pulsars all around us, we see the signals from these pulsars arrive earlier or later, depending on whether space is being stretched or squashed. So we're pretty sure we're starting to see a signal. That's a 25-year-long project that's been running now, where we're just starting to see the signals from these colliding supermassive black holes. What's E. Merlin up to? This morning, we observed the aftermath of something called a tidal disruption event for a research group at the University of Granada in Spain. Our telescopes are used by people from around the world. This is a lovely animation of what a tidal disruption event is. It's got some very dramatic music. I don't know who does their animations, this group, but they've got great animations. Some clever computer people. That's a black hole. That's a supermassive black hole thing on the left. So and this is a star. And now we zoom out to look at the star coming near to a supermassive black hole in the heart of a distant galaxy. The gravity from the supermassive black hole stretches the star to its tidal forces, and then it rips the star apart. That's the disruption bit. The stuff falls into the black hole and then shot out in a pair of jets like that, like this picture shows. So these tidal disruptions events have only been recognised recently. One's happened recently, and we're monitoring it now with our radio telescopes to look for the radio waves that are coming from that event. I think this animation just finishes with a little zoom into one of the jets, which shows you this is the gas from the disrupted star falling in towards the black hole, heating up, spinning, and shooting this stuff out. And in there's a little neutrino, which is a tiny sort of ghost particle that is very hard to detect, which was detected from one of those. What are we doing at the moment? Right this minute, this afternoon, we're actually using the E-Merlin network, that's the network of telescopes across the UK, to observe something that was discovered with this spacecraft. This is called the Einstein probe. It's launched by the Chinese Space Agency, but it's a project in collaboration with the European Space Agency and the Max Planck Institute in Germany. It's actually looking at a flash of X-rays, visible light and radio waves. This is the visible light. Can you see the black dot in the middle where the red lines point at? This is what we deal with in real astronomy, little tiny black dots. That flash we managed, the scientists involved here managed to get the distance of this from a spectrum, and they found that light has been traveling for 12.5 billion years. So this thing's arriving now. This event happened 12.5 billion years ago. It was either an exploding massive star or it was one of those tidal disruption events. So that's being observed right this minute. Very last slides. I have no idea what time it is, and I've no idea whether I've run over my time. 22, oh, perfect timing. You'd think I'd done this sort of thing before. Okay, so what are we doing? What's about the future? I've only had time to show you a few things, right? There's many more things like this happening just in our group in the Jodrell Bank Centre here. We use telescopes all around the world and in space, including these ones. Meerkat I showed you a picture of in South Africa, picture from it. The JWST in space you've probably heard of. There's another spacecraft called Euclid that's just released its first results. We use these things to study all types of stuff. I've not even mentioned dark matter or dark energy or all these other amazing things that we work on. We're nearing first light on that square kilometre array telescope I mentioned at the beginning. The global headquarters is at Jodrell Bank, remember? And we're getting close. By the end of this decade, we'll have first light on that telescope. And the dishes in that computer-generated picture on the top are in South Africa. And the arrays, the aerials on the right-hand side of that picture are in Western Australia. So that'll be the most sensitive, most powerful telescope in the world, radio telescope in the world. And here in the UK, we're just keeping our fingers crossed because it was discussed by the Research Council yesterday, I think, or the day before, about our request for funding for a major new telescope here in this country, which will basically be a set of dishes which are based on the ones that will be for that square kilometre array in South Africa, and a whole bunch of radio antennas like the ones in Australia, but we spread them across the country between Cornwall and Moray, which is by Inverness, and we're going to use that to do radio astronomy at much sharper views than we can do currently with our E-Merlin telescope, looking at space weather, the sort of thing that produced the Northern Lights. Who saw the Northern Lights a few weeks ago? Honestly, it was amazing. If you didn't see it, hopefully it'll happen again. The sun's pretty active, so we'll keep your fingers crossed. But things like that, how the sun affects the environment, space environment, and also looking at space debris and satellite traffic in the environment around the Earth. So that's a major new project that we hope gets funded. But anyone who's ever asked for funding for things knows that you can never be sure whether you get it or not. But we've always got some ideas. And I finished. Thank you. Luckily, I did leave a bit of time for questions, so that's handy.
Hello. I wondered, because in transit, we want a minimum of 3 occurrences of the same event to be sure that it is indeed a transit. Do you have a limit as well for radio, where you want X number of occurrences to be sure, yes, you did detect something, and no, it was not just a microwave thing? Again.
By transit, do you mean a planet orbiting another star, right? So,
yeah.
So we find planets orbiting other stars by one of the really simple but effective ways of finding planets around other stars is if you happen to be looking at this. I don't mind buzzes now and again, you know. So there's a star and there's a planet going around it, and okay, if it's oriented like this, then every orbital period, the planet passes in front of the star. So if you measure the brightness of the star, you see dip, dip, dip. So what the questioner was saying was that if you're looking for these things, you look for 3 transits. Unfortunately, with our stuff, you know, if they were regular like that, the best example of that are those pulsars, so those things that do the flash. So in those cases, what I didn't say, I played you one example, and that was flashing about every 0.7 of a second or something, I think. We see typically they're every few seconds. That's the time it takes that dead star the size of a city way more than the sun to spin. Some of them spin, the fastest is 700 and something times per second. So imagine a dead star the size of a city weighing more than the sun spinning 750 times a second. If I played you the sound of that, it would go. I can't do it now. I used to be able to. I can't get my voice that high pitched anymore. But it's worse than that buzz, I tell you. That buzz was a bit like the crab pulsar in the middle of the Crab Nebula. So those are the best things for repeated things. And then because they're happening if you're looking for planets around other stars, they're probably transiting every few days max, but maybe every tens of days. We can get 100 flashes a second. So we're pretty good on that. Other things, sadly, these tidal disruption events, they happen once in one object. You see the flash, and then what you have to do is catch them and they fade away. So a lot of modern astrophysics is looking at, can we get instruments that will react to things very rapidly? So if something explodes and it produces a flash, lots of other telescopes have to be able to point at it as quickly as possible to get as much information as we can, because you don't get to see that one object do it again, you know. If that helps. Was this? Oh, yes.
Yeah, I'm a big fan of the 3 body problems. The Santi. So I just when the telescope, I'm quite interested in the signal wave you just showed present to me about the pulsar signals. I just want to know if that telescope have a capability to detect extraterrestrial intelligence.
Yeah, I mean, I haven't talked about extraterrestrial intelligence, so I would be. I've done a little bit of work on it. I've got a colleague, in fact, the director at Jodrell Bank is a big extraterrestrial intelligence searching person internationally. We've never detected any signals from extraterrestrial intelligence. We would have told you, I promise. We definitely would have tweeted it, or whatever you call it these days. Yeah, but yeah, radio signals. That's why when they first saw it, they called it LGM1. I mean, for fans of science fiction, which you sound like you might be, there was a film called 2001: A Space Odyssey, and that was released just after the first pulsar was discovered. And if you sort of use any web search tool to search for 2001: A Space Odyssey pulsar Arthur C. Clarke, who was the person who helped write it, you'll see him talking at some press event for the launch of 2001, where he refers to the first discovery of the pulsar and says astronomers are getting excited about this flashing thing. It could be extraterrestrials. This film is all about the discovery of a signal. So he then goes on to talk about 2001. So it's quite an interesting crossover between real science and culture. So yeah, we think extraterrestrials exist. Many of us do. We don't know whether they're sending us any signals. We don't think they've been here, but we're not absolutely sure. The age of the Earth is a very 4.5 billion years. Stuff gets eroded away pretty quickly. don't believe everything you read, you watch on Ancient Aliens, but you know, there's some possibility that something might have passed by here at some point in the past. We just haven't found it yet. Yeah.
What benefits are you hoping to get from the SKA observatory when that comes online?
So the SKA's got, it's one of the, some of these some telescopes and instruments, like anything, are sort of often, sometimes they're single purpose, so they're designed to do one particular thing. But often we have telescopes that will do many, they're intended to do many things, and that would be true of SKA. So it's got a science program that has at least 5 main topics, and they range from cosmology, so looking at the early universe, looking at how dark energy and dark matter affected the evolution of the universe. Dark matter, for those who don't know, is something that has mass but doesn't produce any light. So you can't see it by light, whether that light be visible light, radio waves, X-rays, or whatever. You know it's got mass because you can see how it affects things near to it by its gravity. So there's dark matter. We still don't know what that is. It was first discovered in the 1930s. And it's our particle physicist. There's one of them speaking here tomorrow. He needs to get a move on. Brian needs to get a move on, and his colleagues need to find some. They need to find some particle that will explain dark matter, but we don't know yet. We discovered something, and that is far more prevalent than normal matter. So there's more dark matter than normal matter. And then we discovered something a few years ago that said that instead of the universe slowing down as it expands, which is what it should have been doing, the universe is expanding since the Big Bang, but the gravity between all the stuff ought to be trying to pull it back together. So you'd expect this expansion to be slowing down because gravity is acting against the expansion. But instead we found that it was speeding up, and this is like anti-gravity. It was just mad, really. And so we didn't know what that caused that, so we made up something else called dark energy. When I say made up, I'm doing that in a self-deprecating way. Make sensible suggestions about what might cause these things. But the name that was given to it was a bit of a joke, because if we had dark matter, we didn't know what it was. Dark energy was another thing, we didn't know what that was. And in fact, the bit of the universe that we do know, the stuff we see around us, the atoms we're made of, is about 5% of the total mass energy of the universe, whereas dark energy dominates and dark matter is a bit less than dark energy, but certainly more than normal matter. So all these projects will be done by people using SKA, and I won't have time to go into them all, but loads of things. How stars and planets are formed, we study those things as well. So there's amazing amounts of work going to happen with that telescope. Who's live? Oh, it was the person at the back, I think. Sorry.
Hi.
I don't think anybody can hear you if you don't have a microphone.
First light. That's good. Sorry, apologies. Yeah. Thank you, Tim. That was a really good, interesting talk. I wondered about nearing first light. You mentioned on the square kilometre array.
Yeah.
I just wondered what you meant by that. Perhaps it was simple.
It's just a nice poetic phrase that we use for telescopes. Okay. It means when the first light passes through a telescope. So it's the first observation made with a telescope. Okay. So the first light would be passed through a lens if it was a visible telescope, or bounce off a mirror. Or in the case of radio waves, we just call them first light as well.
Sure.
So basically, yeah, when we first get the first signals, and usually there's some sort of press release, and we say, oh, we got the first. And usually we'll think of something important to point it at that we know will give a nice picture or whatever it might be.
Thank you.
That's what first light means.
And then the other quick question, I suppose, is on the point about extraterrestrial life. How do we know that they're going to be communicating in radio waves?
We don't.
We
don't. And that's the problem, right? Yeah. So you could spend your whole life, as some people have, searching for signals from extraterrestrials, and you may never find them because they may not exist. If they do exist, they may not be communicating. They may be using some other technique. But I think it's a good thing to look for, just in case it's there. And usually, if you look anywhere, what you're doing is you're developing your techniques, your instruments, your computational processing techniques. These days, using some form of machine learning to process the signal, to look for patterns in the signals that we might not see ourselves. There's huge amounts of data that are produced by these instruments. So they're really great technical projects that have spin-offs anyway, but we don't know. We don't know if they're extraterrestrial.
Thank you very much.
I think we'll have one last question, if that's okay.
Yeah.
How is a dark hole made?
how is a black hole made? Yeah, good question. So I mentioned, do you remember me mentioning neutron stars? So these pulsars, the spinning thing with the beams, the cosmic lighthouses. So when a star explodes and the central bit runs out of nuclear fuel, that central bit collapses in on itself. Stars like the sun, so when that happens to our sun, won't be for a while yet, about 5 billion years, but when that happens to the sun, the thing it will make will be a thing called a white dwarf. So the thing collapses in, and a white dwarf is about the size of the planet Earth, and again weighs about as much as the sun, or in the case of our sun, it will produce one that's about half the mass of the sun. The rest of it gets spread into space. But this white dwarf is produced. As I say, about the size of the Earth. The reason it stops there and doesn't fall any collapse farther in is because of something called electron degeneracy pressure, which was discovered by an Indian astrophysicist many years ago called Chandrasekhar. And he worked out that basically when the electrons in this thing get squashed together, some weird quantum mechanics effect happens that exerts a pressure that stops you pushing them any closer. So it sits there at that size. That's what a white dwarf is. If you had a more massive star, then the weight of that star is so great as it collapses in, it can overcome the electron degeneracy pressure. In fact, if that central thing's more than about 1.5 times the mass of the sun, it's called the Chandrasekhar limit, it collapses again, it collapses further, and it becomes this neutron star. It becomes something the size of a city, but weighing more than the sun. And the thing that stops it then is something called neutron degeneracy pressure. So exactly the same sort of thing, but for particles called neutrons, which are inside atomic nuclei. So you make things that's something like a giant atomic nucleus the size of a city, which is what a neutron star is. This is why it's the last question. So if we go any more massive, then even the neutron star can't hold itself up. We currently don't know of any new physics that will stop that neutron star collapsing to what's called a singularity, a point of infinite density, which is a black hole. I don't think points of infinite density can really exist. I'm sure there are people who say they do, but it's hard to imagine something that's infinitely dense, everything concentrated to a single point. But we can't see it, because as soon as that stuff collapses in, if you squash the sun down to be about the size of about 3 kilometers across, it would become a black hole. And whatever happens inside the black hole, you can't see, because no signal can get out, because nothing can escape a black hole. So whatever's going on in there, we can't directly see. So we have to try and understand them by what's happening around them. Does that answer your question? Thank you. Right, we should probably finish. Thank you.